Hi everyone. So last time we talked about alkenes and alkynes. Now let's look at the structure of benzene. Okay. So benzene, representation of benzene. Benzene molecule is like this. It's like a hexagon. And it also has alternate double bonds, 3 double bonds. We call this as a resonance form. Okay, there are 2 resonance forms. And they have alternate single and double bonds. We can also represent the benzene ring like this, indicating a resonance hybrid hexagon with a circle in the middle. That shows the delocalization of electrons. So these are not localized. Since it's resonance, you can see the alternate single and double bonds. So the electrons are delocalized like this. Okay, and if this is the benzene ring, so you can see sigma bond. This is a sigma bond plane, which is these bonds. There is sigma bonds between each atom. Okay, and then in addition to that there are 3 pi bonds, and these are the delocalized pi cloud above and below of the plane of the sigma bond plane. Okay. Now, how do we name these aromatic compounds? So, the benzene ring containing compounds are called aromatic compounds. The systematic naming of aromatic compounds, in which benzene is the main structure, is straightforward because attached groups or substituents are named as prefixes. However, many common names are also still in use. Now, this is that there is a methyl group here, CH3 group. So we call it as methylbenzene. And the common name is toluene. And then when you have 2 methyl groups adjacent to the carbon, you can say 1,2-dimethylbenzene. One of these is going to be 1,2-dimethylbenzene. Orthoxylene is the common name. And then you can have 1,3-dimethylbenzene. And then the common name is metaxylene. Or you can have 1,4-dimethylbenzene. Common name is paraxylene. Okay. Types of organic reactions. Addition reactions. Now these organic molecules can undergo reactions. One type is called addition reaction. Addition reactions occur when an unsaturated reactant becomes a saturated compound. Remember, the unsaturated compounds, when they have double, triple bonds, could be between carbon-carbon or carbon-oxygen. These undergo addition reactions. In each case, it is the pi bond that breaks. So when you have a double bond, there is a sigma bond is there always, and then you have 1 pi bond in this case. And in a triple bond, there is 1 sigma bond and 2 pi bonds. Here also 1 sigma bond and a 1 pi bond. It's always the pi bond that breaks, leaving the sigma bond intact. Sigma bond is more stronger. It cannot be broken easily. In an addition reaction, it's the pi bond that breaks. So this is the type of a reaction that would undergo. Let's say you have this alkene, you are adding X and Y reagent, XY. So the X and Y will add across the carbon-carbon double bond. X goes to one carbon, Y goes to another one. Now this is unsaturated compound, becomes saturated. No more double bonds anymore. Note the carbon atoms are bonded to more atoms in the product than in the reactant. Carbon here bonded to hydrogen, this R group, and carbon. 3 things. Now it is bonded to 4 things. A very common color test that we can do to find out if a compound has a carbon-carbon double bond is the bromine test. Okay, so here this glass or this beaker has a carbon-carbon double bond containing compound in it. Okay, So bromine here is brown in color. Bromine react with a compound that has a carbon-carbon bond. In the beaker, you have a compound with a carbon-carbon double bond, and its orange-brown color disappears. You see here bromine is brown in color. Your hydrocarbon with a double bond is in the beaker. So you add bromine. The container does not become brown immediately because the double bond adds the bromine. So then the bromine is not going to exist as bromine liquid. Now it is being added to the carbon-carbon double bond. So the color disappears because it's used up by this alkene. When all the alkene that we have here is been completely used up, when you keep on adding bromines, just like a titration, when all the carbon-carbon double bond has been saturated by bromine, then when you start adding more bromine, it will become brown in color because there is no more alkene in the beaker to react with bromine. Okay, so it's a common test to find out if a compound of interest has a double bond is that we can react with bromine. If the color disappears, then we know that it has a double bond or a triple bond. Okay, so we learn about the addition reaction. Now we're going to learn the opposite of that, that is the elimination reaction. Elimination reaction occurs when a saturated reactant becomes unsaturated. So this is saturated compound, no double bonds. It becomes now unsaturated compound. So this is the reverse of addition. The groups typically eliminated are hydrogen and a halogen atom or hydrogen and a OH group. So this Y and X are going to eliminate. It could be a hydrogen and OH. What can we make with hydrogen and OH? Water molecule. It could be a removal of a water molecule, or it could be a removal of a acidic molecule like H and Cl will make it HCl, giving alkene. So that type of a reaction is called elimination reaction. The driving force for an elimination reaction is the formation of a small stable molecule such as HCl or water. Okay, now here's an example. You have a saturated compound. This carbon has a hydrogen, this carbon has a hydroxide. You react this molecule with sulfuric acid. So it will remove this water molecule HOH and become alkene. Okay, so this is the ball and stick model of this reaction. Another one, so we learn about the addition, elimination, substitution reaction is the third type. Substitution reaction occurs when an atom or group from an added reagent substitutes for one attached to a carbon in the organic reagent. So carbon in the organic reagent attached to X here, and then you add Y. So Y is going to substitute X now. So Y become attached to carbon and X eliminates. Okay, the carbon atom at which substitution occurs may be saturated or unsaturated, and X and Y can be many different atoms. Okay, you could be different atoms for X and Y, but it is a substitution reaction. One comes and substitute, and then the other leaves. The main flavor ingredient in banana oil is formed through a substitution reaction. Let's look at this substitution reaction. Here you have acid chloride, CH3CO, Cl, we call it as acyl chloride. And here you have an alcohol. Okay, so what's going to happen? This oxygen goes and attach to this carbon and it leaves chlorine. So chlorine is being substituted by this alcohol. You see this blue color oxygen connected to the carbon, and then the hydrogen is lost and then this hydrogen react with HCl, chlorine, to form HCl. Okay, and this is the ball and stick model representation of the same reaction. So this is a substitution reaction. Recognizing the type of organic reaction. Let's see. State whether each reaction is an addition, elimination, or substitution. Now tell me what is this one. Here we have alkyl bromide. So when carbon hydrogen group is like this, we call it as alkyl bromide. What happened here? Have a double bond. What is this? Is it elimination, addition, or substitution? It had eliminated HBr, Br from here and hydrogen from here. So which is a elimination reaction, right? And here you have a double bond. You add hydrogen and the double bond is gone. Now this is an unsaturated compound became saturated. What is this reaction? That is addition reaction, right? Hydrogen is being added onto the double bond, became now saturated. Here we have CH3COBr, CH3CH2OH. Now oxygen here attached to carbon, this one, and H and B are eliminated, right? So bromine is not there, so instead you have this group. What is that type? That is a substitution, right? So the bromine is substituted by this alcohol part. Okay, so that is a substitution. Okay, so those are the three types of reactions: addition, elimination, and substitution. Now we have functional groups in organic chemistry, and functional groups are the ones that mostly undergo reactions when we dealing with organic compounds. Okay, so we can classify these organic compounds according to their functional groups. A group of atoms bonded in a particular way. The functional groups in a compound determine both its physical properties and its chemical reactivity. Functional groups also affect the polarity of a compound and therefore determine the intermolecular forces it exhibits. Functional groups define the regions of high and low electron density in a compound, thus determining its reactivity. And we also talk about oxidation and reduction in organic chemistry. So we know oxidation is loss of electrons, reduction is gain of electrons in when we dealing with the electrochemistry. Okay, even though a redox reaction always involves both oxidation and reduction, organic chemists typically focus on the organic reactant only. Okay, instead of monitoring the change in oxidation numbers of the various carbon atoms, organic chemists usually note the environment of electron density around a carbon atom by counting the number of bonds to more electronegative atoms, usually oxygen, or to less electronegative atoms, usually hydrogen. Okay, we are not going to count what is the oxidation number of carbon. Instead, what we're going to do is we're going to look at carbon and oxygen. If you take carbon and oxygen, oxygen is more electronegative. The more electronegative element will attract electron towards itself. So then the carbon will lose electron density around the carbon. So when carbon is attached to oxygen, we say that is oxidized. When carbon attached to hydrogen, when it has more hydrogen, hydrogen is not as electronegative as oxygen. So hydrogen is 2.1, carbon is 2.5. 2. Yeah, let's see what carbon. Lithium is 1, beryllium 1.5, 2, 2.5. 1.5 to 2.5. Yeah, carbon is 2.5 and hydrogen 2.1. So there is not much of electronegativity between carbon and hydrogen because it's a covalent compound. Okay, it's a non-polar bond. So when you have more hydrogen, we say it is reduced. Okay. When a carbon atom in the organic reactant forms more bonds to oxygen or fewer bonds to hydrogen, thus losing some electron density, the reactant is oxidized. And the reaction is called an oxidation. Okay. When carbon atom in the organic reactant forms fewer bonds to oxygen or more bonds to hydrogen, thus gaining some electron density, the reactant is reduced and the reaction is called a reduction. So let me show you a reaction. Let's say you have this CH3, CO, let's say CH2. Let me show you oxidation. CH2OH becoming CH3COOH. Let me draw it again. Let's say you have something like this: CH3, C hydrogen here, another hydrogen here, OH, and there is one oxygen. It become CH3, C carbon became double bonded to oxygen, and oxygen and OH. Okay, so here if you look at this carbon has two hydrogens and one oxygen, and when you look at this carbon here, it has two oxygens attached to it and no hydrogens. So this process is called oxidation because the carbon lost its electron density since it now has attached to two oxygens. So this is oxidation. The forward reaction is oxidation. The reverse reaction therefore is reduction. Okay. We're going to learn about this in more detail when you come to organic chemistry. But for now, this is enough. Okay. Okay. So here are some functional groups in organic chemistry, organic compounds, some important ones. Alkene, we knew about it, we learnt about it. Alkene is ene. Prefix or suffix name is alkene. And this is the Lewis structure, ball and stick model, and the systematic name and the common name. Ethene, common name is ethylene. And when you have a double bond functional group, which is alkyne, ine is the suffix. And this is an example, that is ethine or acetylene. Alcohol functional group is OH group. All is the prefix name. And this is methanol, methyl alcohol. And then another one is called haloalkane. When you have a halogen attached to the carbon, haloalkane, halo prefix, like this. Lewis structure is this one. So this is chloromethane. And this one here is amine. Amine has a nitrogen attached to carbon. Amine, here is an example. Nitrogen attached to carbon, and this nitrogen has two hydrogens attached to it. We call it as ethanamine or ethylamine. An aldehyde functional group is carbon bonded to oxygen as a double bond, and then you have a hydrogen. That is an aldehyde functional group. Prefix is al, and here's an example, ethanal or acetaldehyde. And then you can have a ketone. In a ketone, you have carbon-oxygen double bond, and then you have two carbons on the either side of this carbon-oxygen double bond. Ketone, prefix on, and 2-propanone or acetone is the name. And when you have a carbon-oxygen double bond and OH group attached to it, that is called carboxylic acid functional group, oic acid. The name would be ethanoic acid, or the common name for this particular one is acetic acid. And then when you have a carbon-oxygen double bond, oxygen like carboxylic acid, now instead of a hydrogen, you have another carbon. We call that as an ester. Okay, the prefix would be O8 and methyl ethanoate or methyl acetate. So this is a ester functional group. Amide functional group would be you have a carbon oxygen double bond and then this carbon attached to a nitrogen. That is an amide. And then the CN triple bond cyano group would be nitrile functional group. Ethane nitrile or acetonitrile. So let's look at a little bit in more detail these functional groups. Alcohol functional group consists of a carbon bonded to OH group. Alcohols are named by replacing the E at the end of the parent hydrocarbon name with the suffix -ol. If it is methane, you remove the E and then you add -ol, this would be methanol. If it is ethane, it would be ethanol. Propane, it would be propanol, like that. Alcohols have high melting and boiling points since they can form hydrogen bonds between their molecules. Reactions of alcohols. Alcohols undergo elimination and substitution reactions. Now this is an alcohol, right? So you can remove the water molecule. So there are hydrogens on these points. Remember, these are carbons and carbon can form 4 bonds, 1, 2, and there are 2 hydrogens here. So there are 2 hydrogens, one here, one here. So when you lose this HOH as water, it can form an alkene, cyclohexene. So alcohols undergo elimination and substitution. Okay. And this one over here, you have an alcohol. It reacts with this potassium dichromate and sulfuric acid. And it become a ketone like this. Okay. So that is in fact an oxidation reaction. Because here this carbon has hydrogen, one hydrogen and one oxygen. Now it lost its hydrogen here in the product. Now you have a pi bond, double bond with the oxygen. Okay. So the name of this compound 2-butanol, this is 2-butanone. So this OH is now being substituted by oxygen. Okay. So these are some examples that has alcohol functional group. Methanol or methyl alcohol, byproduct in coal gasification, de-icing agent, gasoline substitute, precursor of organic compounds. And 1,2-ethane-diol or ethylene glycol, main component of auto-antifreeze. Serine is an amino acid found in proteins. And cholesterol, you can see that there is all part in it because it has alcohol, and the alcohol in cholesterol is right there. So this is the cholesterol molecule. And the next functional group, haloalkanes, meaning alkyl halide. You have organic compound and then you have a halogen. Haloalkanes are named by identifying the halogen with the prefix on the hydrocarbon name. The carbon bearing the halogen must be numbered. So this should be numbered. Remember, the halogens are your group 7 elements: fluorine, chlorine, bromine, iodines. So these haloalkanes, they undergo substitution and elimination. So here, if you have this 1-bromobutane, this molecule with hydroxide, bromine or the bromide would be leaving and hydroxide would attach to carbon. So basically it is a substitution reaction. Okay. Instead of bromine, now you have hydroxide group or the alcohol group OH. Also it can undergo elimination. So here you have a chlorine and you're going to react it with potassium ethoxide. So this is going to act as a base to remove HCl, hydrogen chloride, and become alkene. KCl. It will be eliminating potassium and chloride, making potassium chloride, and then the elimination will take place. One hydrogen from here and the chloride will leave. Okay, so you will form an alkene. So this is an elimination reaction. And then the amines contain nitrogen atom next to the carbon. Systematic name for an amine is formed by dropping the final E of the alkane and adding the suffix amine. If it is methane, methanamine, ethane, ethanamine, like that. Common names that use the name of the alkyl group followed by the suffix amine are also widely used. So this is the general structure of amines. Amines can in fact classify according to the number of alkyl groups directly attached to the nitrogen atom. So this is your nitrogen atom. Nitrogen will be attached to the carbon and this nitrogen can have hydrogens on it. If you have hydrogens on it, we call it as a primary nitrogen. Primary amines are RNH2. R is the carbon where nitrogen attached, and on the nitrogen you have two hydrogens. RNH2 primary amine. When one of the hydrogens are replaced by another alkyl group, they are secondary amines. R2NH. When all two hydrogens are replaced by alkyl groups, we call them as tertiary amines. So basically tertiary amines doesn't have any hydrogens on nitrogen. So these are some of the examples that with the nitrogen functional group or the amine functional group. So this is lysine, which is an amino acid, and this is adenine, component of nucleic acid. You can see NH2, and then epinephrine. This is a secondary amine. It has only one hydrogen. Neurotransmitter in brain, hormone released during stress. And then you can see here nitrogen with 3 carbon groups attached to it, which is a tertiary amine. Brain stimulant, cocaine, widely abused drug. Properties and reactions of amines. Primary and secondary amines can form hydrogen bonds. We learn about hydrogen bonds in General Chemistry 1. They therefore have higher melting and boiling points than hydrocarbons or alkyl halides of similar mass. So amines normally have higher boiling points because they can form hydrogen bonding, and they are higher than hydrocarbons or alkyl halides. Tertiary amines does not have a hydrogen on the nitrogen, so it cannot form hydrogen. They cannot form hydrogen bonds between their molecules because they lack a polar nitrogen-hydrogen bond. Amines of low molar mass are fishy smelling, water soluble, and weakly basic. So you guys can identify that you are eating fish, that you have fish by the smell of the fish. That fishy smell is due to a nitrogen containing compound, amine, due to the amine. Amines undergo a variety of reactions including substitution reactions. Predict in the reactions of alcohols, alkyl halides and amines. Determine the reaction type and predict the products for each reaction. So here we have alkyl halide. You adding sodium hydroxide. What do you think is going to happen? So hydroxide can substitute for this I. So then you will have a substitution reaction, and instead of I, you will see an OH group attached to carbon. Okay, like this, OH group attached to that. Okay, and then the next one, you have an alkyl halide, and then you have an amine group. So this one also, again, nitrogen here can go and attach to carbon and eliminate bromine. So that can also undergo substitution reaction. Okay, and then the product will look like this. This is a substitution reaction. Instead of a bromine, bromine is now removed, so the nitrogen will attach to this carbon. Okay, CH2, CH3. And this is the secondary product. And then the last one, you have this CH3, CH, CH3, OH group, dichromate and sulfuric acid. And this is an oxidation reaction. So this will become this product over here. So this is an elimination reaction, since acidic dichromate is a strong oxidizing agent. So you would remove hydrogen and form carbon oxygen double bond, which is a ketone. So that is an elimination reaction. And then alkenes. Alkenes, we came across alkene before. It contains carbon-carbon double bonds. Typically undergo addition reaction. The electron-rich double bond is readily attracted to the partially positive hydrogen atoms of hydronium ions and hydrohalic acids. Now this is our alkene. When you add a hydronium ion, so hydrogen and OH can add across the double bond. So the hydrogen goes to here, and then the OH goes to this one. So that is a addition product. Okay, and then you have alkene here. You can add a hydrochloric acid, and that will also be added across the carbon-carbon double bond. Okay, so this is again the addition product. When HCl adds to alkene, you will have this product right there. And then aromatic hydrocarbons. Remember, the aromaticity is due to the benzene ring. Benzene is an aromatic hydrocarbon and is a resonance hybrid. Its pi bond electrons are delocalized. Okay. Aromatic compounds are unusually stable. Although they contain double bonds, they undergo substitution rather than addition reactions. Even though benzene has 3 double bonds, and those double bonds are resonance stable, so they will normally do not undergo addition reactions. Instead, it will undergo substitution reactions. Bromine, with benzene ring, in the presence of this iron bromide, forms, the bromine will add to the benzene ring. So before the bromine adds, there are hydrogens here, 1 hydrogen at each carbon spot. Now hydrogen will be substituted by bromine. Okay, that's a substitution product. And aldehydes and ketones, these are some other functional groups. They contain this carbonyl group. Carbonyl group is carbon-oxygen double bond, carbonyl group. Aldehydes are named by replacing the final E of the alkane name with the suffix al. If this is ethane, it would be ethanal, propane, propanal, butane, butanal, like that. So it has a carbonyl group and a hydrogen. Ketones also has a carbonyl group. Now, instead of a hydrogen, it has a carbon group. Basically, 2 carbon groups attached to carbonyl group. Okay, they have the suffix on, and the position of the carbonyl must always be indicated. Now, since the aldehyde going to be a hydrogen next to the carbonyl group, it's going to be a end. Aldehyde you will find at the end of a molecule, yes, in the structure. But the ketone should be between two carbons. So we have to represent, or we have to indicate when you are naming which carbon carries the carbonyl group. Okay. These are some common aldehydes and ketones. Methanol or formaldehyde, used to make resins in polywood, dishware, countertops, biological preservative. And ethanol or acetaldehyde, narcotic product of ethanol metabolism, used to make perfumes, flavors, plastics, other chemicals. And this is benzaldehyde, artificial almond flavoring. And this carbonyl group is polar. So we are still learning about the carbonyl group. So this carbon, oxygen, carbonyl group like this has a sigma bond and a pi bond. Okay. And this is the two R groups. And then this is the oxygen with two lone pairs. It has a sigma bond and this is the pi cloud. Okay, and oxygens are normally electron negative, electron rich. So oxygen carries partial negative charge and carbon will be partially positive. Carbon oxygen bond is electron rich and is also highly polar. It readily undergoes addition reactions and the electron poor carbon atom attracts electron rich groups. Okay, so if you look at here, the resonance, carbon oxygen pi bond can be resonance with carbon being positively charged and oxygen being negatively charged. Since this is positive, electron rich groups can attach to this carbon and undergo addition reactions. Here are some examples of aldehydes and ketone reactions. Reduction to alcohol is an example of an addition reaction. So here you have a carbon-oxygen carbonyl group. Reduction means you're adding more hydrogens onto this one. So it will become cyclobutanol, which is an addition reaction. And then organometallic compounds, meaning organic compounds having a metal, which have a metal atom covalently bonded to carbon, add to the electron poor carbonyl carbon. This is alkyl lithium organometallic compound. This is our aldehyde and then the carbon is positive, oxygen negative. Here lithium is a metal, they carry partial positive charge. As a result, alkyl group carries a partial negative charge. So this negative end can attract to positive carbon. So then this alkyl group attached to carbon. And then the carbon hydrogen pi bond breaks and then lithium goes to oxygen. And then when you add water, the lithium falls off and then oxygen take up hydrogen and become alcohol. Okay, that's how ketones and aldehydes react with organometallic compounds in addition reactions. Predicting the steps in a reaction sequence. So here, for each, fill in the blanks in the following reaction sequence. For each step, we examine the functional group of the reactant and the reagent above the yield arrow to decide on the most likely product. So now you are adding hydroxide to bromine. What can happen is this could be a substitution reaction. Hydroxide would be substituted for bromine and this will become OH. That you can draw that that product over here, and then you are reacting with dichromate and sulfuric acid. Alcohol that you're going to form here, when you react these two reagents, it will become a ketone. Okay, and then I will show you the product, and then that ketone, something like this, can react with alkyl lithium like this. Add this methyl group onto the carbon, and then when you add water, it can become alcohol again with a one added methyl group like this. Okay, so the first step involve alkyl halide reacting with hydroxide. You see here, substitution reaction to butanol. Substitution reaction which yields an alcohol. In the next step, the alcohol oxidizes to a ketone. With these are oxidizing reagents. It oxidizes to give you a ketone, carbon-oxygen carbonyl compound. And then when you add the organometallic compound, this methyl group attached to carbon, and when it adds water, this become OH. Okay, so that is how we can use these reagents to get a compound of interest that we want. Okay, and we can also identify whether it is a substitution, elimination, or addition reaction, and what each reagent is doing, and how the functional groups are changed from each step. Okay, so here is a haloalkane. Functional group became alcohol, then to ketone, and then again an alcohol with one methyl group added. This is how we use organic chemistry and the reagents to make something we want from something small compound. Okay. Okay, another functional group is carboxylic acids. Carboxylic acid contain this functional group, carbon-oxygen carbonyl group and OH group. And they are named by replacing the E of the alkane with the suffix oic acid. If it is ethane, it would be ethanoic acid. Propane would be propanoic acid, like that. Carboxylic acids are weak acids in water and react with strong bases. So this is a carboxylic acid, weak acid, react with sodium hydroxide. This is a base. And this is the acidic hydrogen. So the hydroxide will take up this hydrogen and become carboxylate anion and sodium ion and water. So how do you form the water? You have this OH, it takes up this hydrogen and become water. These are examples of carboxylic acids. Methanoic acid, irritating component of ant and bee stings. Butanoic acid found in butyric acid. Odor of rancid butter, suspected component of monkey sex attractant. And then you have benzoic acid, aromatic acid. Calorimetric standard, used in preserving food, dyeing fabric, curing tobacco. And then octadecanoic acid or stearic acid, found in animal fats, used in making candles and soaps. And then we have ester. In the ester functional group, so this is a carboxylic acid. In the carboxylic acid, if you react the carboxylic acid with an alcohol, it's going to lose a water molecule. OH from the carboxylic acid and hydrogen from the alcohol lose a water molecule and become an ester. RCOOR. Okay. Ester groups occur commonly in lipids, which are formed by the esterification of fatty acids. And then we have amides. In the amide functional group, you have a carbonyl group and a nitrogen attached to it. Amides like esters can be hydrolyzed to give carboxylic acid and an amine. So you find this kind of bond, carbonyl group and a nitrogen, in peptide bonds in proteins, which links amino acids in a protein is an amide group. These are some molecules with amide functional group. Acetaminophen. You see here acetaminophen, you find amide functional group. NN-dimethyl methanamide or dimethyl formamide. It's an organic solvent used in production of synthetic fibers. You see here. nitrogen and the carbonyl group. And this one, lysergic acid diethylamide, which is a potent hallucinogen. It also has this amide functional group. So these functional groups we find in nature also. Predict the reactions of carboxylic acid family. Predict the products of the following reactions. So you have a carboxylic acid and you have alcohol here. What is going to happen when you mix these two together? This OH group attached to this carbon and leaves this hydroxide group with hydrogen, removing a water molecule, and then forms an ester like this. Carbon oxygen forms the bond with oxygen and it forms an ester. Okay, and then the next one, you have B. So this compound, carbonyl group and NH. So this is amide functional group. So you're adding sodium hydroxide and water. When you add, what's going to happen is it's going to break this bond between this carbon and the nitrogen. We call it as a hydrolysis. We can form a bond and also we can break a bond. So here when you break, so with this reagent it's going to break this bond. Okay, so the hydrolysis of amide, so it's going to give you from left side carbonyl group with oxygen and from the right side you will get an amine. Okay, so don't worry too much about these reactions. We're going to learn more in detail about these reactions when you come to organic chemistry. But for us in Gen Chem 2, just get to know that there are these type of reactions are happening in organic chemistry. Okay. Functional groups with triple bonds. Alkynes contain the electron-rich carbon-carbon triple bond, which readily undergoes addition reactions. Propyne alkyne with hydrogen, it can remove one of the pi bonds and give a double bond. A triple bond became a double bond. And you give more hydrogens, you add more hydrogens, it will become completely saturated, propane. Another triple bond is a nitrile carbon-nitrogen made by substitution reaction of an alkyl halide with cyanide. Alkyl halide with cyanide form a triple bond. Okay. Recognizing functional groups. Circle and name the functional groups in the following molecules. So this one here, you have a carbonyl group and OH, and this is carboxylic acid. Carboxylic acid. And here you have oxygen and carbonyl group, and this is, there is a carbon here and a carbon here. So this functional group right here is ester, functional group. And this whole ring is aromatic benzene ring. And this one is, you guys know that's an alcohol. And then here you have nitrogen with carbons on it. So that is a amine functional group. In fact, that's a secondary amine. Okay, amine. And this one here, it is a ketone with carbon, oxygen, carbonyl group. And this is a haloalkane. And this is alkene, double bond, which is a alkene. Okay. Carboxylic acid, ester, alcohol, secondary amine, ketone, haloalkane, and this is alkene. Okay, that concludes our session about organic chemistry.